So all I've done now is I said, okay, great. I wanted to integrate this. I have no idea how to integrate that. But now I have this, don't I? That's what this is. So we're really, this is where you have two options. Would you like to integrate the power series, or would you just like to write out the power series and integrate each term? Your choice. I don't care. Nobody cares. So I'm going to do it both ways, right? So option one would be to do this. Take the integral of this power series. And how do we integrate power series? dx. I need dx here at the end. How do we integrate a power series? We did that last class. Power rule. All you do, all you do is the power rule. So my antiderivative here is going to be some constant I don't know, plus, all right, sigma, sum n equals 0 to infinity. Now remember, this is our c sub n, right? That's our c sub n. So that doesn't change when you integrate. That stays the same. Negative 1 to the n over n factorial. But what does the x to the 2n become? X to the 2n plus 1. And then over 2n plus 1. That's just power rule, isn't it? If this was x to the 7th power, the antiderivative would be x to the 8th power over 8. Right? That's our basic power rule. So that's the answer.
Is that 2n plus 1 or 2 sub n plus
2n plus 1.
Okay.
Now, just for the sake of doing it, let's write out a few of these. So this is equal to c plus, all right, what do I get when I let n be 0? When n is 0, what do I get here? Negative 1 to the 0 is 1. 0 factorial? 1. Okay. X to the 0 plus 1. X over 1. So you just get x. Now let n be 1. What happens when you plug in 1? You'll get a negative this time, won't you? And then over 1 factorial, which is 1. So it'll be minus 1 over 1, x to the 3rd over 3. Next one will be a plus, won't it? X to the what? 5th. Yeah, so you'll get, when you're plugging in, where are we right now? This is plugging in 0, this is plugging in 1. When you plug in 2, you get a positive over what? 2 factorial. Don't forget the 2 factorial. And then x to the 5th over 5. I'll do 2 more on this. What would the next one be? Plus or minus? Minus 1 over, where are we? 3 factorial, x to the 7th over 7. I'll stop there. Plus dot, dot, dot. That's the antiderivative of e to the negative x squared. That was option 1. Option 2 would be to take this and not replace this with the power series written in sigma notation, but to actually replace this e to the negative x squared written out first, then do the antiderivative. So take this right here, not this one, take this one, let's write out the first few of these. So let n be 0, what do you get? You just get 1. And the next one will be minus. Now I'm plugging in 1 into this. So negative there, 1 factorial is 1, x to the 2nd power. Now I'm letting n be 2. So I'm going to get a plus 2 factorial. Yeah? X to the 4th. Minus 1 over, where am I? 3? 3 factorial, x to the 6th, and then so on and so forth, right? dx. Do you see a difference between these two methods? The first method, I wrote the series in here, I integrated the series, then wrote out that series. Here, I'm writing out the series before I integrate it, and now I'm going to integrate each of these one by one. So what's the antiderivative of 1? Well, we'll have a plus c, right? But x, right? What's the antiderivative of this? Minus 1/3 x cubed, right there. What's the antiderivative of this? Well, 1 over 2 factorial covered it up. What's the antiderivative x to the 4th? 1/5 x to the 5th, this right here. But then we have the 1 over 2 factorial in front. So you're getting the same answer. Do you see that? Same answer. So it doesn't matter which way you do it. All right. So with this tool, right, with this tool, in theory, we should be able to integrate anything. As long as we can come up with the Taylor and Maclaurin series for a function, we should be able to integrate it. Because we should be able to integrate powers. All right, so now the next part, part B, says, you know what? How about a definite integral? So how do you do a definite integral? So what if I change the problem to be integral from 0 to 1? Well, you still find the antiderivative, don't you? Right here, you find this antiderivative, but we no longer put plus c because we're doing a definite integral. And at the end, we just put in the evaluation bar 0 and 1, right? Now, it does dot, dot, dot forever, so it's impossible for you to actually plug in 1 dot, dot, dot forever, but we would stop somewhere, maybe the first 20 terms and stop, and then plug in 1, then plug in 0, get an answer. You want a better answer, go out the first 100 terms. You want better, go out the first 1,000. So I'm going to show you on the computer real quick what happens if you go to Wolfram Alpha.
So,
Yeah, go ahead.
From 0 to 1, that doesn't just mean plugging 0 and 1 for n and stop writing the terms after that?
No. 0 to 1 means you still have to find the antiderivative, which is an infinite series. And then you have to plug 1 in and plug 0 in, which you can't do unless you stop somewhere.
Yeah.
And that's up to you. So if I go to Wolfram right now and I say, hey, Wolfram, let's find the antiderivative of e raised to the negative x squared. I've shown you all this before. We know that it gives us some crazy answer, right? This error function. It's like, what? What the hell does that mean, right? But if I go here and I say, you know what? Give me the integral from 0 to 1 of e raised to the negative x squared dx. It's going to give me a numerical answer without a problem. It's going to give me, can you all see that all right? It's giving me about approximately what? 0.74684? 824? Here's how they got that. The computer plugged a 1 in here, a 1 here, a 1 here, a 1 here. Now, what about plugging in 0? It's going to kill everything off, right? In this case, it's going to kill everything off. So really, it's just plugging in 1. So if you get on your calculator and do 1 minus 1/3 plus 1 over whatever that is, and minus that plus that, and you start doing that, you're going to get some decimal answer. It's going to be close to 0.746824. I don't know how far the computer went out. Pretty far, though. But if that's not an acceptable answer to you, then you can go right here and click more digits, and then Wolfram's going to go ahead and go more digits. It's going to go further out into the infinite series to get a very, very precise answer for you. And you're never going to run out of terms, right? So if you're not happy with that answer, I just go further out, right? And see, this is why these series are so important in computer science, because this is the way a computer works with mathematical functions, through the series, not through the functions the way we think of them. And so the computer can do operations fast, right? Multiplication, division, it can do all this, addition, subtraction. That's all this comes down to now, doesn't it? Okay, I'm almost done. Not really. Shit, man. I need like an hour. I need one more hour. I want to show you all the most beautiful equation in math, but I don't know if I'm going to be able to. This is more important, what I need to show you here. So what I want us to do here is try and find, part A here, find the first three non-zero terms of the Maclaurin series for f of x equals e to the x sine x. So here's what we could start doing. We start making a table, right, and find a formula. But we already saw how bad that got with x squared cosine x, didn't we? And at the end, I pissed you off by showing you could have just taken a little shortcut, right? Well, do you know the Maclaurin series for each of these? I know the Maclaurin series for that, and I know the Maclaurin series for that, don't I? So let me go ahead and write out what they are. And I have to do what with those two? Multiply them, right? Multiply the two. So let's do the Maclaurin for e to the x. It's sum n equals 0 to infinity, 1 over n factorial x to the n. That's e to the x, right? Sine x is sum n equals 0 to infinity, bless you, of negative 1 to the n over 2n plus 1 factorial x to the 2n plus 1. We derived both of those, didn't we? How do you multiply two infinite series like this? Now, when we had this earlier, right, x squared in front of the cosine, remember that? The one you got mad at me about just a second ago? What did we do with the x squared? We just moved it in. And the reason we could do that is because there was only one term here. But you don't have one term out here. You have what? Like in front of this, how many terms are in front of it? An infinite number of them. So how do you multiply infinite polynomials? That's what each of those parentheses are an infinite string of it's an infinite polynomial, right? So how do you multiply them? Well, you're going to have to do this this just kind of grinding technique. First thing I'm going to do is I'm going to rewrite this sigma notation. I'm going to write out the first, 5 terms of what it is. So start plugging in 0, then 1, then 2, then 3, then 4. So if I plug in 0 here, we did this already, you get 1. And then if you plug in 1, you get x. If you plug in 2, you got x squared over 2 factorial. Remember me doing that? And then it was x to the third over 3 factorial. Plus, one more, x to the fourth over 4 factorial. Plus, and it goes forever, doesn't it? That's e to the x. All right, what about sine? What would we get if we wrote this out? Well, remember, sine is odd, right? Sine is odd. So it's going to start with odd powers. What's the first odd power of x? X to the first power. So we have x, then it's going to alternate. Minus 1, or x over 3 factorial, x cubed over 3 factorial. I'm going to write it like that instead. Then 1 over 5 factorial x to the 5th, then minus 1 over 7 factorial x to the 7th, plus dot, dot, dot. Now those are on your table, like on your sheet, right? Like right in front of you, you have those. So on the final, in a week, if I ask you to multiply two power series like this together, you don't have to write this down. You can just write each of these down. I just wanted to make sure you understood that when you have two series next to each other multiplied, you can't just take this and slap it inside here. You can't do that. You can't, all right? You cannot. So how do we multiply things? How do we multiply polynomials? Remember FOIL was cute, right? FOIL is cute when you have two things times two things, FOIL. We're going to do the same sort of thing, but it's not called FOIL here. It's called multiplying infinite polynomials, all right? So we're going to follow the same pattern. How do we do it? We start with the first one and do what with it? Multiply through the whole thing. So I got to do the 1 through here, then here, then here, then here, and forever, right? So I'm going to have to stop at some point and just be like, okay, that's it for now. And then I'm going to move on to the next one. And then do the next one through there, through there, through there, through there, and then stop. And then move on to the next one. And do that, do that, do that. And you all just do it until Wednesday of next week and see what we get, right? No, let's do it. You ready? Multiplication. So the first multiplication is 1 times this. Well, it's just going to be all that, right? So I'm going to write it down, but watch the way I write it. Okay, I left some spaces there for a reason. You'll see in a minute. Notice I left spaces because it is possible that when I continue to do this, it is possible that I might get some x to the fourths in here and x to the sixth, so I'm leaving some space. Y'all agree that's my first multiplication?
Yes.
Okay, so 1 is done. Now I'm going to do the x through. X through. When I do x to this, what do I get? X squared, which I should add it down there, like at the end of these dots, right? I'm not going to do that though. I'm going to line them up vertically. So I have x squared, don't I? And put it right here in this column for x squareds. Then what do I have? X times this minus 1 over 3 factorial x to the fourth. I'm going to put it right here. Minus 1 over 3 factorial x to the fourth. What's the next one? 1 over 5 factorial x to the sixth. And then one more. Minus 1 over 7 factorial x to the eighth. Do y'all see why I left those spaces now? Now I'm going to move on to the next one. Okay. Here to here. It's an x cubed, right? And it's 1 over 2 factorial x cubed. I'm going to line it up right here. 1 over 2 factorial x cubed. Lining up my x cubes. What would the next one be? Here to here. Shit. Well, x to what power? I'm doing this one to this one. X to the fifth, so I know it's here. What's the number in front? I'm doing these two, right? It's 2 factorial times 3 factorial, isn't it? I'm actually going to write it that way. 1 over 2 factorial, 3 factorial. Now, what am I being asked for here? Only the first what? First 3 non-zero terms, which means that I only need the first 3 of these. Here, here, here. I really don't need to worry about all this. I need an x term, an x squared term, an x cubed term. All right? So I'm going to stop with this one for now. And I'm going to think about what happens when I go from here to here. What power am I going to get? X to what? I'm going from here to here. X to the what? Here to here. X to the fourth, right? Which is over here somewhere. But remember, I only want the first 3 terms, right? The question is, when do I stop doing this, right? If I only want the first 3 terms, when do I stop getting contribution over here? Have I reached that point now? I have, right? When I go from here to here, it'll be x to the fifth, then x to the sixth, then x to the eighth. Those are down there. Y'all understand what I'm doing? So I'm satisfied with just these right now. Now, good thing I didn't want the first 8 terms, right? Because then you'd have to go way out. I'm only going to ask you for like 3 on the test. So now, what's my answer? The answer to this is that it's equal to x plus x squared plus, we got to put these two together, don't we? We got to put those two together. And just as a side note for us, what we're really doing there is we're doing minus 1/3 x cubed, and we're adding to it, what? 1 over 2 factorial. 2 factorial is 1/2 x cubed. And now you need a common denominator, don't you? So, what is this?
5, 6, 4, 6.
See, we get to this point where I forget it. 1, 6. What's the final answer is what I'm getting at. When you put those together, what do you get? Plus 1/6 x cubed. Plus dot, 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 right? Dot, dot, dot. It keeps going, but we're only getting the first 3 terms. You all right? So if you go back and you look at our notes, we had to integrate this at one point in time. Does anybody remember this problem? It was a special one. This was the one I called the rabbit out of the hat, where you're trying to find this integral, and then you wind up seeing it again on the other side, and then you have to move it back over, and this is a weird problem, right? What we could actually do now is not integrate that, but integrate that. And if we had more terms, then we could do it, right? We could get more terms and get as precise as you ever want to. So I'm going to go back to Wolfram for a second because I want to show you a feature that you may or may not be aware of. But if I type in e to the x times sine x, and just type that in and hit enter, Wolfram will give you a lot of just random information about this. It'll probably graph it for us. That graphs it, treats it like a function. I don't know what it's doing there. Gives you some alternate form, the roots, blah, 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 blah. Ah, series expansion. Look at that. Wait a minute, hold on. What's wrong?
Is that a 0 or an O?
Don't worry about that for a second. Hold on. Why is ours 1/6 and theirs is not? It was 2 factorial, but 2 factorial is 2.
Yeah.
What's going on? Oh, is that a 3 factorial?
Yeah, that's supposed to be.
Hold on. Where did this one come from? That was this one?
It is supposed to be 3 factorial.
Mm,
Probably the 1 times the negative 1.
Oh, no, 1/3 factorial x cubed times x.
oh, I never, no. This times x is x to the 4th. That's this one.
That was the first one where you first put the 1 in.
Yeah.
1.
Times the.
Oh, this is 3 factorial.
Yeah.
Shit, everyone. Okay, good. The universe is still here. Okay, so this should have been, what should this have been? 3 factorial, which is 6. And now put them together. Okay, and this will become 1/3. God, I'm glad I typed that in. I would have had a mistake up here. This is what happens when I rush. Got it? But isn't that nice? It actually gives you the series expansion. Now that O thing is just telling you that they are.
Is that big O?
It's not. No, it's not. I know big O is like order count, like for like operations. That's not what that big O means. This big O is just telling you the order that they've gone out to. So look, where did they stop? They're saying that that's accurate up to the 5th power. So you know how I said the first 3 terms? That only gave us x to the 3rd power, right? They only go out to x to the 5th, you see? So they only stop x to the 5th, and then the next thing it says plus, and then all that other shit after that, which would be the order of 6 on. That's all that means. It's like a remainder. Okay? Okay. One more. Find the first the first 3 non-zero terms of the series for tangent x. Maclaurin series. Well, is it on your table? Do you have it on your cheat sheet? Do you have tangent on there? Maclaurin for tangent? It is on there? Inverse tangent's on there, right? But not tangent. Well, we got to get it ourselves then. So then all we have to do is remember that tangent by definition is just sine over cosine, right? And you know the series for each of those. So you have to take the series for sine. Let's write the series for sine out. But let's not write it in sigma notation. Let's write it out term by term. Sine was odd, right? So x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th, right? Minus 1 over 7 factorial x to the 7th plus dot, dot, dot. That's sine. And you are doing what with it? Dividing it. Dividing it by the cosine, which is 1 minus x plus x squared over 2 factorial minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial plus dot, dot, dot. Right? That's sine over cosine.
Where did the minus x come from?
I don't know why I put this in here. Sorry. I'm rushing. It's 1 minus x squared over 2 factorial plus minus plus. Okay, that's right. There we go. That's what we had for cosine, right? All right. So look, when we multiplied, you just did like a FOIL thing, right? It's cute. How do you do this? Can't do a reciprocal, sorry. Long division. You have to do long division. Yeah, you have to do long division. So let me show you how this works, because this looks weird and it's a skill you need to know. Moving on. Because I promise you, you'll be in a class, they'll have a ratio, right? This is a ratio of two infinite series. And the next line that you get from this, you would never see how it happens unless you did long division. So when we do long division, you always start with the numerator in the box. So I'm going to put the numerator in the box. X, I'm going to leave a space, minus 1 over 3 factorial x cubed, plus 1 over 5 factorial x to the 5th, minus 1 over 7 factorial x to the 7th. I'm leaving the spaces for the same reason I left the spaces a second ago. On the outside is what you're dividing by. I'm going to put that out here. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, 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 right? And now you play the same game that you always play with long division. You start by looking at the very first term, and you say, what do I need to multiply that by to get that? X. So I just put an x up here. Doesn't matter where you put the x, I'm putting x here. And now you're going to take that x and you're going to multiply each of these by x and line them up where they go. So what's x times 1? X. Okay, what's x times that? Minus x cubed over 2 factorial, right? I'm going to write 1 over 2 factorial x cubed. Notice I lined them up with the x cubed. Okay, now when I do this x times this, I get plus x to the 5th over 4 factorial. So I'm going to write plus 1 over 4 factorial x to the 5th. I'll do one more. This times this, minus x to the 7th over 6 factorial, so 1 over 6 factorial. You'll see what I did? Yeah? Now, how does long division work? You come through and you take this line and do what with it? Subtract it, changes the signs. That becomes a minus, that becomes a plus. That becomes a minus, that becomes a plus. And now you're adding down. These go away. Okay, what does this become? Okay, hopefully I won't screw that one up now, right? That's minus 1/6 x cubed plus 1/2 x cubed. Isn't that the same one we did a second ago? Yeah, same answer. That's what I'm saying. Is that what you're saying? The same thing we just got in the previous?
Well, last time the 1/6.
Yeah, no. I'm saying this should be minus 1/6. Not that the answer should be. Yeah, this should be minus 1/6, right? That's this.
It should be something over 3, right? Because
It's 1/3. Yeah, it's 1/3. That's the same thing that I screwed up on a second ago. I accidentally put 3 here, not 3 factorial. So this should just be what? 1/3 x cubed? Okay, we need to do this one as well. Crap, that sucks, doesn't it? I'm not going to because of time. I'm not going to, okay? I would do this one and then maybe one more. Okay, so I have something here and then something here, right? Now, what would be the next step? What do you have to multiply this by to get this first one?
1/3 x.
Plus 1/3 x cubed. And then you take that and multiply it here and here and here and here, and you're going to get the next line. And then you do it again. And you stop at the third one because I asked you for the first 3. So because I only have 4 minutes, I think that's where I'm going to have to stop.
So the top line would be the first 3 terms. And then you
That's right.
Okay.
You would stop when you get 3 up here.
Just put plus, dot, dot, dot.
Yep. Yes.
Is this going on the formula sheets, or would we have to put this on the cheat sheet?
I'm okay if you use this on the test. The one with the how to do Taylor McLaurin. I'm okay with that.
Can we move
Yep.
the sheet for our test?
Yes. I said that at the beginning of class. So I'm going to go to Wolfram. I'm typing in tangent x. I just typed in tangent x and I'm scrolling down and there's the series expand. Whoa, there's the series. There's the series for it. See it? We were on our way. We had x, we had 1/3 x cubed. The next one would have been 2 over 15. So that's how you get the series. So I've shown you here at the very end, at the last moments of the class, I've shown you how to take two infinite polynomials and multiply them and then also divide them. Unfortunately, I didn't have enough time to show you the most beautiful equation in math, but you can look up, there's videos on it, and it's a really good application. And I actually have it worked out. In our notes, I actually have it completely worked out, the most beautiful equation in math. I go through the entire workout of how it happens and how you can show that that equation is true. Okay? I'm very sad that I didn't get to show you that. I'm extremely upset.
Can you show us in Cal 3 with the logarithm equation?
Yeah, in Cal 3 I won't be able to. We won't have time. But it's something, it's a 10-minute thing we can sit down and talk about. It's pretty cool. All right, so see you in a week, right? And bring your formula sheets and be ready. You have a review, right? I've provided you a review. It's due as a quiz grade. 2 quiz grades? 1. 2 quiz grades, right? I have a couple of those. Anyone else need one of these? How to do it, Taylor McLaurin? There's donuts.
Did you pass out papers on Monday?
I didn't pass out. I will give you everything at the final. If you need something, the reason I didn't pass out like your exam corrections and all that is because I don't think you really need those for what your test is over, right? Your final exam is really what, chapter 8? Almost exclusively chapter 8. So I will give you all your stuff back on the day of the final. Oh, an extra one of those. These are $5. The other ones are free. Yes?
Do you guys have any other previous exams, final exams, that I can also use as more?
I don't know. I mean, not that I'm just going to be able to produce right here for you right now. Yeah, I mean, the idea of the review is for you to look at the problem, go, okay, can I do it? Yes, you do it. Now you go look in your homework for problems similar to that problem. I mean, that's really the way you should be looking at the review. The review should never be like, you look at the problem and say, I need to be able to do that problem. It's more of, hey, look, he's asking for me to be able to do interval of convergence. I better look at the homework for interval of convergence, make sure I feel comfortable with those problems. So your more review is just go look at homework, really. All right, well, it's been fun. Have a good luck on all your finals. My office hours next week are not what they are normally, because like you're in class at different times, right, next week than you normally are? Like we'll be here from 9 to 11:45. So same with me.